everyone, and thank you for attending this session. I'm Stéphane Jankowski. I'm lead data scientist at Ubisoft. And today I'm going to talk about FastCat and how it's impacting CRC operations with deep learning. So today's menu is pretty straightforward. First of all, we're going to add a bit of context around the project FastCat. Then we'll talk about the methodology. And finally, how we deployed it and how we made sure that it was impacting the CRC. But before that, just a few words about Ubisoft. So Ubisoft is a video game company. It's the #1 French video game editor, and it's a worldwide leader in the entertainment industry. Today is more than 18,000 people, around more than 40 different studios, a bit everywhere in the world. Ubisoft made more than 2,000 billion euros in sales for fiscal year 2018-2019. And the same year, the player have spent nearly 5 billion hours playing in our worlds. And speaking of our worlds, I'm sure you already know some of them, but we have a pretty eclectic portfolio of brands, let's say, from Assassin's Creed to Rayman, Rainbow Six, Just Dance, and so on and so forth. And more specifically about data science at Ubisoft, it's a bit everywhere. So I'm giving you some examples, but it's pretty much everywhere in the different departments at Ubisoft. But it could be, for example, in the production, so in the studios that made the video games for stuff like balancing, for in-game personalization, content generation, or improving in artificial intelligence. Like many companies, it's also used for marketing purposes, for personalization, for recommendation, for any kind of targeting. We also use data science for security, for example, for detection, to also assist the security specialist, but also for tracking in-game toxicity, for example. And finally, we also use it for customer support. To improve player experience, to improve automation, to add more automation and add more security to the CRC process. And that's actually where FastCat comes in. So a bit of context. FastCat stands for fast categorization, so the name says it all. But before to deep dive into the projects, let's talk about how a ticket is created when a player has a problem in our ecosystem. So let's say that we have a player playing in our ecosystem, in our world, and whenever he faces an issue, whether it is while playing a game or while trying to connect to our platform or while trying to buy something on the store, whatever, he can go on the customer support portal and create a ticket describing in plain text what's going on, what's happening. After that, the ticket goes to what's called the triage process, which is basically assigning some metadata to the ticket, saying what it's talking about, what it's about. Then it goes to the queuing process, and finally to the resolution process, so the ticket is resolved by a skilled agent for this specific task. What's going to be of interest for us today is the triage process. So I said that it was assigning some metadata. It's actually assigning a hierarchy of metadata from the most generic one, which is the main category, to the most specific one, which is the context category. So for instance, the main category could be technical issue. A subcategory is a bit more accurate, something like crash or freeze. And then we know a bit more about the issue with the context. We know that it's on launch, for instance. So assigning this metadata before FastCat was 100% manual. It took a lot of time for the CRC agents. And well, let's say that it's not the most interesting part of customer support compared to, for example, actually resolving the issues. So FastCat is a system powered by AI that can automatically classify a ticket in its corresponding context category. So it's based on NLP, on natural language processing. It uses deep learning to predict the right metadata among about 250 different categories at the most granular level, which is the context category level, only based on the player's text, the player's input. So what's behind FastCat? What is the methodology behind FastCat? Well, we had two successive approaches, let's say. The first successful model that we had in place was a model called ULMFit for Universal Language Model Fine-Tuning for Text Classification. which went out in 2018, and it was one of the first successful application of transfer learning in NLP. It's LSTM based, and it gave us some very good performances with even few data per category. So that was really interesting to use. It worked pretty well for the English language, but as it was successful, the customer support wanted us to apply this methodology to all the different languages that they had on their portal. However, for us, it meant that we had to train one single model for each language, which just makes it impossible to maintain in the future. So we had to find an alternative, and especially a model that could handle all the languages at once in one single model. So we thought about the transformers that seemed like a relevant approach to do that. So let's talk about the transformers models, and more specifically about BERT, which is the model that we've used. BERT is an NLP algorithm. It's a pre-trained model that is pre-trained on two different tasks, actually. The first one is the mass language modeling task. It's basically just removing a word from a sentence and trying to predict it back. So it's a language model, and it's trying to just understand what's going on in a specific language. And it could also be trained on a different task, like the next sentence prediction, which is less relevant for us right now. It's more done for stuff like question answering and that type of stuff. It is just a language model, so we can actually use it to fine-tune it to many different NLP and NLU tasks. You name it: translation, question answering, name entity recognition. In our case, of course, it will be classification. It is attention-based, which means that it's really trying to weight every word, to give importance to every word in the sentence, and more specifically to find the relationships between the different words in the sentence, which is very important and really different from an LSTM-based type of modelization, for example. And finally, it's bidirectional, which is actually the B in BERT, meaning that we are not only looking at what's before or what's after a word to make its context, but we are looking at the whole sentence to really try to capture the meaning of the word and its context in the sentence. But actually, we did not only use BERT as is, but we also add a bit of knowledge distillation to the mix. So what's knowledge distillation? It's actually a way of compressing a model to make it faster, to make it easier to use, while maintaining similar performances to the original model. So it's a methodology that could be applied to any type of machine learning model, but it's particularly useful, and it really makes sense in fields like deep learning or any fields where you have like pre-trained models that get bigger and bigger, like NLP, computer vision, etc. And actually, this is a pretty interesting graph to show you why knowledge distillation is useful. So we can see that we have a bunch of algorithms that were created in the past couple of years. And we can see that we went from models in 2018 like LMO and GPT that had around 100 million parameters in their architecture, to model like GPT-3 more recently that is close to 200 billion parameters. So that's really getting huge, and distillation could really help us, working with those very huge models. And to give you an example, the model that we've used for FastCat, which I'm going to talk in a minute, it's called DistillBERT. It's around 66 million parameters, so it's way smaller than any of those models that you can see here, but it's still pretty close in terms of performance. So it's a good trade-off between size and performance. How does distillation work? Well, it's actually a pretty simple methodology. First of all, you need what's called a teacher model. So you need a model that you want to replicate, a large model that performs well and generalizes well. That's the teacher model. You want to replicate it. Then take all the data that you have and compute all the predictions using your teacher model, and you end up with what we call the knowledge. And the predictions itself are called the soft labels. And finally, use this knowledge and use those soft labels to train a smaller network, smaller in architecture. And that's the student model. So for instance, if you have a new data point that is coming in your system, on one end, you predict this data point with the teacher model. That's you are generating the soft target for this data point. On the other end, you are feeding this data point to the student model and then computing the loss between what's coming out of the teacher model and what's coming out of the student model. Then you compute your loss, you compare the two outputs, and you use the backpropagation to train and improve the student model. So you end up with a student model that's really trying to replicate the behavior of the teacher model while being way smaller in terms of architecture. So that's a really interesting methodology here. So now if we combine, on one hand, the transformers model and more specifically BERT with knowledge distillation, we end up with DistillBERT, which is the combination of the two. DistillBERT is the same architecture as BERT, except that we've reduced the number of layers by a factor of 2. Initialization is pretty straightforward. We're just picking one layer out of 2 in the teacher model, so pretty simple. The data used for training is exactly the same in both cases. And as for BERT, DistillBERT is optimized and trained using the max language modeling task, which is the one where we remove a word in a sentence and try to predict it back. So we end up with a model that's 40% smaller than the original BERT, 60% faster than the original BERT, while maintaining 97% of its capabilities, of its predicting power. And this 97% is computed on the usual benchmark that we can find in the literature for NLP. So we've applied DistillBERT for FastCat and for the ticket categorization task. And we've used it for 9 different languages so far, and there's more to come. And we can see that we have some very good performances for all the 9 different languages for the top 3 accuracy. It's pretty stable. We don't have one language that is way worse or way better than the other one. It's pretty consistent across all the languages. So that's really interesting since it's only one model that handles all the languages. We also have a feedback system in place where CRC agents can actually give us some feedback when they think that a prediction that was made by the model is wrong. And we use this feedback to actually retrain and improve the model in production. And this way, we've improved the English top 1 accuracy by 32% in a few months, and 24% for the German top 1 accuracy. So that's some pretty good improvement right here. And we were also able to compute a very significant return on investment for the CRC because we actually were able to automate this whole triage process phase. So this return on investment was computed based on agent time that was saved. I won't go into too much details on that since the numbers are pretty much confidential, but let's say that everybody was pretty happy with the project. All right, so let's now talk about deployment and how we put that model in production. Well, it all starts with code, of course. So we have some code on a GitLab repository. Then we have a CI/CD process that does 3 successive tasks. The first task is the building phase. So we are building 2 images, 2 Docker images here. The first one is the images that we will use to train the model, to train a new instance of the model, for example, to update it. And the second image that we are going to build in there is the serving image, so the one that contains the API that will be used by the CRC. Those 2 images, once they are built, they are pushed to a Docker image repository, which is called Quay. And once those images are built and pushed, they are deployed. So on one side, for the training image, the images are deployed on Kubernetes pods that will handle the training. Those pods are created on very specific instances that contain GPUs and have a lot of RAM and computation power, because those models that we are training need this computational power. Once the model is trained on this Kubernetes instance, it's saved on HDFS in a model repository. On the other end, we deploy the serving image on another Kubernetes instance, where we have actually a lot of different replicas of the same API serving image. So we have many different replicas of this image that will allow us to easily handle any peak of activity. For example, when we have a lot of tickets coming in, if there's a specific bug, for example, then we will be able to manage the workload on all the different replicas and be able to have a good response time, even in case of emergency. And so all those replicas, all those serving images will look in the model repository on HDFS and look for the right model based on a configuration where we say, okay, in production, we want this model to be in production. And well, these replicas and these pods deployed on Kubernetes are the ones that are going to be pinged and queried by Salesforce, which is the tool that the customer support uses. So all those Kubernetes servers are created using something called Ubisoft Kubernetes service, which is the internal Kubernetes service that we have at Ubisoft. So let's talk a bit more about that. Just a quick glance at what we call UKS internally. So it's really a way of providing a lot of different features around cluster management, around Kubernetes, through different tools, but the main one is one called Rancher, which allows you to do plenty of stuff, alerting, login, monitoring your workload as well. And we have also other tools around Rancher, like Grafana, for example, to do some nice dashboarding and nice monitoring as well. But UKS is also a nice way of using Kubernetes on-premise, so on the internal cloud that we have at Ubisoft. We can also use UKS with different cloud providers, AVS, GCP, you name it. But it's particularly interesting for our on-premise cloud. So we are pretty happy with this solution. And finally, we had to put in place a bit of monitoring around FastCat. So we actually created two different dashboards. The first one is more of a business dashboard, let's say. Is built with Tableau, and it's used by both the CRC, the end users, and the data scientists to monitor the performance of the model. So what we want here is to understand how the model is behaving. We want to assess performance. We want to see where the model is doing good, where the model is doing bad, how it's evolving in time, how are the different versions of the models better than the previous one, and so on and so forth. And on the other end, we have another dashboard, which was made using Kibana, which is more of a technical dashboard to monitor the health of the API, right? So we want to spot technical errors. We want to monitor response time to see how workload is doing. And it's more used by the data scientists and the data engineers in the project. So that's it in conclusion. So really FastCat led to a better handling of tickets for Ubisoft CRC, thanks to this automation of the triage process. Notice also that we have other data science projects and initiatives going on at Ubisoft to bring more automation and better user experience for our players. And finally, there are plenty of other aspects of CRC where we could also apply some machine learning. For example, for bringing more security to their activity, like for example, to verify account ownership, to spot phishing attempts, that kind of stuff. So that's it for me, and thanks a lot.